All right, everyone, welcome back. Let's go ahead and get started. We have a lot to cover today, but first, let me just say that I'm so glad you guys are here. I know it's a holiday, so I appreciate you all being here. All right, so we are at a very, very exciting point in the course because not only have we started full swing on visualizing patterns in nature and really understanding the basics of how to create generative art on your own, but as of today, we are past the midpoint of the course. So a quick roadmap for today. I wanted to take you through some of the visualizations that we've created so far and really show you the connections between them. I thought that'd be a nice thing to do just because we have finished about 6 or so hours of lecture so far. And then after that, we'll get into the patterns for today, talk about the visualization. There's going to be a lot of coding, and so we will have to move just a little bit more quickly than we normally do. Please don't let that stop you from asking any questions if you have them, but rest assured this is being recorded, and so if we move just a little too fast through something, maybe a line of code or two, then the recording is always going to be available for you to go back and look at that. All right, so that being said, let's go ahead and start by taking a look at some of the connections between the patterns that we've created so far. So if you'll recall, we've really focused on 5 different visualizations so far in the course. The first being that random walker that we created in lecture 1. And then in lecture 2, we kicked things off with bouncy balls and coffee cups. And then last lecture, we talked a little bit about chaos and fractals. And so we did the chaos game and fractal trees. Now, at first glance, there's not a lot that ties all of these visualizations together, especially not in terms of the code, until you look just a little bit closer. And what I really want to show you guys is that a lot of the techniques that we used to create our random walker, we used again when creating our bouncy balls, and we use them again when creating our fractals. And there's lots and lots of different connections in this course. And if you understand just a few key concepts that we're going to be going over, you'll have the ability to create tons and tons of visualizations across so many different domains. A good example is randomness, right? We saw randomness pop up with our walker, which was super simple and didn't really visualize anything in nature. But then we saw randomness again playing a really, really big role with the chaos game, which visualized fractals and snowflakes that we absolutely do see in nature. Similarly, coordinate systems and coordinate planes, those are going to be important when we're doing something as simple as creating a random walker, but then we saw them useful again when we were creating the points around our circle for the coffee cup example, and then we really messed with them a lot when creating our fractal trees using more advanced functions like push and pop matrix. The other thing that I want to point out is the level of math that we've been doing has been relatively consistent. Everything has been algebra and trig. We haven't gone past what you might learn in like a very standard high school math course. And the last thing that I want to point out is that every single one of these visualizations has had a ton of what ifs associated with them. And as you guys know, that's a really important part of this course, asking what if something was just a little bit different and being able to take that what if and turn it into a piece of art. All right, so that being said, today we're going to be covering cellular automata and artificial life, which we'll talk about in just a second. But I wanted to show you the connections that we have with today's visualizations and as they relate to like all of the visualizations that we've created so far. So with cellular automata, we'll be messing a little bit more with coordinate systems, and then we'll hopefully be spending the vast majority of today's lecture creating an artificial life simulation called Boids, and there we'll be pulling a lot of stuff that we used in lecture 2 with our bouncy balls, thinking about forces and vectors, and using a little bit more algebra and trig and object-oriented programming. All right, so that being said, let's get into today's lecture content. We're going to spend just a few minutes with the slides, and then we'll go over to the code as we normally do. But we're going to start with cellular automata. And so you may have heard of cellular automata before, especially if you've taken a computer science class or a biology class. But the idea is relatively straightforward. Cellular automata just refers to a grid of cells that have some state, and that state changes as a result of some local rules being imposed upon our cells. So if you really just think about a grid full of squares, and each square can have one of many different states. For today's purposes, we'll only be talking about Boolean states. So each cell can either be dead or alive, true or false, however you'd like to think about that. But this grid consists of some states, and those states evolve over time. And the really important thing is that they evolve as a result of local rules, right? So my state as a cell is going to be dependent on the states of the cells that immediately surround me. If there's a cell way over there in the grid that I can't see, that has no relationship to me, then I'm not going to be directly affected by it. But what's really interesting is that local behavior, this very self-centered behavior, leads to really, really cool global patterns. And there's lots and lots of interesting rules in patterns. We're only going to be focusing on one today, but that's totally fine because the nature of cellular automata is such that once you know how to code out one, it's very, very simple to expand that idea and code out anything that is useful to you. I also want to spend a second talking about the GIF that you see on the screen here. This is not a typo. This isn't left in from the old slides where we were talking about Sierpinski's triangle. This is actually something that we can create using cellular automata. Rule 90 is a rule for cellular automata that creates Sierpinski's triangle. And that's just one of those really fun connections that we see throughout the course. The coffee cup example gave us the Mandelbrot set. The Mandelbrot set was a fractal. Another fractal is Sierpinski's triangle, which we're able to create using cellular automata. And so there really are just bountiful connections here. All right, so we want to focus specifically today on something called Conway's game of life. This is going to be a specific type of cellular automata. It is by far the most popular cellular automata, and it was created by a mathematician named John Conway. He was a really, really cool guy. If you guys haven't heard of him, definitely check out some of the stuff that he did. He died relatively recently as a result of COVID, which was really, really sad. But this is something that he's very, very well known for, and it's a really cool game. The idea is that we want to use cellular automata with Conway's game of life to simulate life, death, and population dynamics. Now, while that's the explicit sort of reason that Conway's game of life exists, that's what the cellular automata seeks to show, we also see Conway's game of life being a good model for all sorts of other things, like bacterial growth in food, or the growth of infected blood cells in the human body, or even ant colony behavior, which is really interesting for reasons that we'll talk about in just a second. The other cool reason why I think it's fun to study Conway's game of life in this lecture is because it's Turing complete. The patterns that we can generate with Conway's game of life can be used to create logic gates. Those logic gates can be used to create a computer, and this entire process is Turing complete, which is really, really cool. So how does Conway's game of life work? Well, there are a couple of basic rules, and we'll take a look at a visualization on the blackboard in a second, so that you guys have a better understanding of what this process looks like. But the rules are super simple. Again, you have a bunch of cells. Each cell is either alive or dead, and the state of the cell depends on its neighbors. So if a cell is alive and it has 2 or 3 neighbors, then it's good, it's thriving, it has a good social friend group, it has people around it to provide it with resources, and so it stays alive. Now, if a cell is alive, but it only has 0 or 1 neighbors, it dies due to underpopulation. Maybe there's just not enough people around. We can contrive all sorts of very good reasons why a cell might die with very few neighbors, but maybe we leave that to you for now. Similarly, if a cell is alive and it has 4 or more neighbors, then it dies due to overpopulation. It's very easy to contrive a reason why this might be the case. If there's some finite amount of resources that must be shared amongst a small group, having too many people within that group causes cells to die because they don't get enough resources. Now, there's also a way for dead cells to become alive, and that is if a dead cell has exactly 3 neighbors, then it becomes alive as a result of reproduction. Okay, so that's Conway's game of life. It's super simple. We'll come back to this in a couple of minutes. I want to touch on artificial life in, I think, exactly 2 slides, and then we'll hit the blackboard, really understand what all of this stuff means, and then code it out. Okay, artificial life. So it turns out cellular automata is a subset of artificial life. And artificial life more broadly simulates systems of natural life. This might be how birds flock, or fish school, or ant colonies behave. And we'll talk about all of those in just a second or two. So what's different about artificial life is, unlike cellular automata, it's not restricted to cells, grids, and states. As you'll see with the visualizations that we create today, they're going to look a lot more organic. Now, the other thing that I think is worth mentioning with artificial life is that there is a use case for machine learning or genetic algorithms here. If any of you guys are interested in genetic algorithms, shoot me a text on Slack, shoot me a message if you're interested in messing with visualizations of that stuff. I love genetic algorithms. I think they're really, really cool. They're easy to program. They're a lot of fun. And so, yeah, we won't have time to cover it in this course, but definitely something worth looking into. The other cool thing about artificial life is it's a very rich field with lots and lots of applications. Again, we won't be talking about or showing off all of the applications in lecture just because there are so many and we have such little time, but I would be remiss if I didn't tell you a little bit about the applications. The first that I wanted to touch on is evolutionary art and music. These mainly come from genetic algorithms, and they use genetic algorithms to produce some sort of interesting audiovisual result. The next is electric sheep. If you're not familiar with electric sheep, it has a lot to do with fractals, and this is another one of those cool connections that we see throughout the course, but I would definitely look it up. There's lots and lots of videos and articles explaining what electric sheep is, and I think it's worthwhile to check out. There's a lot of interesting hardware stuff that we can do with artificial life as well. One of the pre-lecture videos today was a video actually from here at Harvard where researchers are using self-assembling robots, and in the most general of terms, that too is a form of artificial life. And finally, artificial life can be used for optimization of functions. Things like particle swarm optimization is very commonly used as a stochastic optimization method. Ant colony optimization is biologically inspired, and those are also really, really cool to take a look at if you have a spare minute. The type of artificial life we are going to be talking about today, though, is going to be something called Boids. It was developed by this computer scientist named Craig Reynolds. I think it's a lot of fun because it's relatively easy to program. We're able to do so with everything that we've learned so far without introducing too much new content, and it just looks so pretty. And the idea again here is that local behavior leads to global patterns. So Boids are a simulation, like I said, of bird flocking behavior, and the idea is that, right, when birds move, they're not considering the flock as a whole. They're not saying, hey, what is my role in this flock? I mean, to some extent they might be, but that's not what's at the forefront of their motives, right? They're thinking, how do I fly with the rest of the birds around me? And that eventually creates all sorts of like interesting and intricate global patterns that we see all the time and that we might find really, really pretty. And so the idea behind Craig Reynolds and his Boids is that every single Boid can see a certain distance around it, just like a bird doesn't have infinite sight. It would only be able to see and gauge what the birds around it are doing. And then each of these birds follow a specific rule, and this rule really determines how the bird flocks. And so there are 3 rules. I'm not sure if you guys can see. I know the projectors aren't showing the images, but they are showing up on my computer. So hopefully we'll get them there in post if you guys can't see them at the moment. But there are 3 rules that Boids need to follow in order to create flocking behavior. They are separation, alignment, and cohesion. And the idea behind each of these is really, really simple. The first, separation, is a rule that forces each Boid away from all of the Boids that are super close to it. The idea is you don't want to be really, really close to another bird or Boid, just in case something happens and you end up hitting them or like having to get really close to them. You want some sort of buffer before you do hit them. And so this pushes a bird or Boid away from the Boids around it. The second rule is alignment, and the idea is that all of these Boids want to move towards the same location. Maybe they're flocking in a certain direction, they're going somewhere, they all want to move in the same direction, and so alignment is a rule that forces a Boid's velocity and like direction to be similar to the velocity and direction of the Boids around it. And the last rule is cohesion. And so the idea here is that every single Boid wants to move to the center of its flock. If there's a group of Boids around it, it wants to be in the center. Again, there's all sorts of like interesting reasons why this might be the case. You can probably contrive of a few. If you've watched my TED Talk, I sort of talk about why this might be the case, because wind speeds might be lower and safety is pretty high in the middle of the pack. And so there's all sorts of good reasons for cohesion to also be a rule that we induce upon these Boids. All right, I think that's it in terms of slides for the day. Yeah, so what we'll do is we will recreate Conway's Game of Life, a visual for that. We'll talk about the math and the code for it, and then we'll recreate Boids, and then we'll call it a day. So let's go back to our Blackboard for a couple of minutes. And we'll talk about how to recreate Conway's Game of Life. So let me go ahead and zoom out here, move over to our processing sketch. All right, so at its core, like we said, Conway's Game of Life is a cellular automata, and cellular automata are played on some sort of grid. Now, for our purposes today, we'll think of this as a square grid or a square canvas. We're used to doing things on a rectangular canvas, but I think a lot of our math will be a lot easier if we think of this as a square. So our width here and our height here are going to be the exact same, and we want to create a grid out of this square. Maybe like an n by n grid, where n is the number of cells along each row and column. So maybe we have a grid that looks a little something like this. Now, as we talked about today, our grid, right, is going to be consisting of cells, each of which have a Boolean state. For the sake of our conversation, we'll talk about them in terms of being alive or dead. In the code, this will manifest itself as being true or false. And in other contexts, this might be some sort of like other Boolean state. And so we need a way of representing each state. So maybe we say a cell that isn't filled in is going to be dead, and a cell that is filled in, maybe it looks a little something like that, is going to be alive. And we want to, like we said, induce the rules of Conway's game upon this grid. So if we originally have a grid that looks a little something like this, then we can figure out what each of these cells should do in their next iteration. So we know that this cell up here, it has 0 neighbors, and so we know that it dies in the next iteration. It dies in the next iteration. This cell has 2 neighbors, and so it's okay, it's happy. And so this cell continues to live on in the next generation. This cell only has 1 neighbor though, and so it dies. Similarly, this cell dies as well. And so in the next iteration of Conway's Game of Life, only this cell right here is going to be alive. And in the generation after that, again, only this cell is the only one in the next generation, and so in the next generation it will have 0 neighbors around it because these 2 are dead. And so in the generation after next, this cell will die as well. So in 2 generations, everything dies off, which is pretty interesting. Now, as you might expect, the game gets more interesting than that if we have a situation where we have exactly 3 alive cells. Okay, actually, I made a mistake. So that isn't exactly what happens. Because recall, this cell right here is dead, but it has exactly 3 alive neighbors. So in the next generation, the generation 1 after this cell will become alive, which means this cell and this cell will be alive. And so they each have 1 neighbor, and so they'll both die. So we, again, won't have anything 2 generations from now, but in the next generation, we'll have both these 2 cells alive. And so as you might expect, we can get all sorts of like very interesting and intricate patterns out of this. But the question is, how do we code it? And so what you might expect is well, we need some sort of way to store data about the grid that we've created. We need some sort of way to say, hey, this cell is alive or this cell is dead. And so the way that we want to do that is by creating a 2D Boolean array, right? And this is going to be what we use behind the scenes to say, hey, the column 0, row 1 cell right here, is that alive or is it dead? And we can get that information very, very quickly using our 2D array. And so that's how we want to store our information. There isn't really a good use case for objects in this case because we can store everything that we need inside of that 2D Boolean array, and so we won't be using objects here. Now, we need to think about what functions do we need. And we probably need a way to display this grid, right? We want to be able to say, hey, this is our grid, this is what it looks like. And then we also want the ability to update our grid. So let's create a function called display grid. And let's create another one called update grid. Okay, so let's talk about how each of these functions are going to work. If we want to display our grid, then we want the ability to create a square. Now, in processing, the way that we create a square is slightly different from the way that we create a circle, so we'll talk about that here. In processing, the way that we create a square, we're going to take in 3 parameters, just the way that we did with circles. But with circles, the first 2 parameters talk about the center of the circle's x and the center of the circle's y. Here with squares, it's going to refer to the top left of the circle's x and the top left of the circle's y, followed by the side length of the square. And so we need to draw a bunch of squares, right? And we'll talk about where those squares need to be. And then we want functionality for updating our grid. And for updating our grid, we're going to be looking at every single cell. We're going to be counting the amount of neighbors that is alive around it, and then updating its state based on whether or not this cell is alive or dead according to Conway's rules. Everybody cool with that idea? Are there any questions about anything so far? All right, awesome. Okay, let's move to the code. Okay, so first thing that we need, as always, is going to be our void setup and our void draw functions. So recall, setup gets run once every time we hit that play button, and then draw is just an infinite loop of what should happen every single frame. So we want to store all of our data in this 2D Boolean array called grid. Now we need to define the size of our grid. We said that this would be an n by n grid, and so n should be some sort of integer, and we'll define how big or small n is in our setup method. We said that we want to play this on a square canvas. That's going to make our life a little bit easier. So maybe we define our size as 500 by 500 instead of our usual full screen. Now we want to say maybe our n is something relatively small like 10. And so then we can say our grid is a new 2D Boolean array that is size n by n, now that we know exactly how big n is. Okay, and I think that will be everything that we need on our setup. Let's move forward to our draw method. So for our draw method, we said that we wanted 2 functions. We always want to display our grid, and then we want to update our grid. Of course, we haven't created these functions yet, but once we do, I think all we need to be able to do is clear our screen, display our grid, update our grid, clear our screen again, display our grid, update our grid, so on and so forth, and this will give us the evolution of Conway's game. Okay, so let's start with that display grid function because I think it's just going to be a little bit easier. I'll go ahead and say display grid, and we don't need to return anything here. This is just going to be for the purpose of display. And for now, we'll comment out this update grid. Okay, so how do we want to display our grid? Well, we know that we want to iterate over every single cell and display that as a square. And so we know to iterate over every single value in our 2D array, we're just going to want to set up a double for loop like this. Those of you familiar with programming have written this thing a million times before. And so what we're doing inside of this double for loop is, so this double for loop gives us an I and a j position, a row and a column position for every single cell within our grid. Now, we want each cell's x value to range between 0 and our grid width, right? We want to interpolate it evenly across that amount. So let's go back to our blackboard for just a second and take a look at what that math might look like. So if we know we want to take n different cells and create a row out of them, and we have the variable width, or w, as I've written on the board here, if we have w, then what is the distance of each x-coordinate such that it lies equidistant from its neighbors on w? Well, we've solved for this before, right? We kind of did this when we were working with regular polygons and putting vertices around a circle. We said that, listen, we know that we have n different cells, so why don't we just say, and remember we're using I and j to go between 0 and n, so why don't we say I over n times our width gives us the x position of our cell. And we know that I, right, I is going to be a value that goes between 0 inclusive to n exclusive, because that's how we've written our for loop. And so this means that this will go from 0 to n minus 1, which means that this fraction right here, is always going to be between 0 and 1. And it's not going to be inclusive on that 1 there because we never get to n here. And if we never get to n here, if we're always less than n, then certainly this fraction is going to be less than 1. Is everybody good with that idea? Perfect. Okay. And so we want the exact same thing with j. Remember, I and j are pretty much super similar in this instance because we're using a square. The only thing that we need to do is swap out I with j and width by height, but width and height are the same. So let's go back over to our code and we'll say, hey, we want to draw a square. And the square's x-coordinate should be I divided by n times our width. The y-coordinate should be j divided by n times our height. And so what should the size of each of these squares be? Well, if we know we need n of them to fit within our width slash height, then each of them should be 1 divided by n times our width, or our height, but I'd show it width here. Right, so I've made a small mistake here. I wonder if anybody sees where the mistake is. It's really small. It is a little bit of Java minutia, and we talked a little bit about this first lecture. So the mistake is we're doing a lot of integer division here. Remember, I we declared as an integer, and n we declared as an integer. And when we define two integers and then we divide them, that is going to give us an integer as the result. Now that's really problematic here because we know I divided by n is always going to be less than 1, and if we truncate that value, we're always going to get 0. And so we're always going to be drawing a square at 0, 0, and then doing 1 divided by n, so that's size 0. So we're not going to see anything. And so what we want, if we want to convert all of this into the floating point space, is just we want to multiply this by 1.0. Because 1.0 is a floating point number, and so Java says, hey, we were working with only integers before. Now we're working with floating points, so our result could be a floating point, and let's make sure that we represent it as a floating point number. Okay, so if we go ahead and draw this, I think what we should see is just a grid of squares. Yep, and indeed we do get a grid of squares, so that's exactly what we're looking for. Now, each of these squares, remember, is a Boolean. They have a state. They initially are all set to false. That's just how Java does it when we create a new Boolean array. But we want to say in the future, sometimes these will be true. They will be alive. And we want to color them differently if they're alive versus if they're dead. And so maybe down here, when we're displaying our grid, we say, hey, if this particular cell, if the grid at cell ij is alive, then we want the fill color to maybe be green. And remember, we're working with RGB space here. So our R channel, our red channel is going to be 0. Our green channel, we're going to crank it all the way up to 255, its maximum value. And our blue channel is going to be 0 here. And now if this cell is not alive, then we don't want to give it a fill. And we can do that in processing very easily. We just say no fill. And so if we run this again, we're going to get the exact same thing. And the reason, right, is because every single cell is dead. They all start out as false. And so indeed, if we run this, we'll see every single cell is dead. It's the exact same thing as before. But what if we randomly said, hey, about half of you should be alive? And we'll determine whether you start out alive or dead based on a random number. So let's use our double for loops again. We want to iterate over every single cell. And we want to say, hey, let's generate a random number, either 0 or 1. And if that number is 1, then you stay dead. But if the number is 0, then you become alive. So every single cell should have a 50-50% chance of becoming alive. And so we say, hey, you're already dead. You've started out as dead. But let's generate a random number between 0 and 2. And remember, this is going to give us a floating point value that is 0 or 0 point something or 1 or 1 point something all the way up to 1.999. It's not going to give us 2, though. It's exclusive on that bound. So you're giving us a floating point number, but we really want an integer, right? And so let's convert this to an integer, and that's going to go ahead and truncate the result of that random number. So anything that was 0 or 0 point something just becomes 0, and anything that was 1 or 1 point something just becomes 1. They have an equal probability of being generated, and so we have an equal probability of getting either a 0 or a 1 when we write this code. And so we'll say, hey, we randomly generated this number. If that number turns out to be a 0, then it is this cell's lucky day because it is going to become alive. And so if we write that, now what we should expect to see is just about 50% of these cells in some sort of random places to be green. And indeed, that's exactly what we get. And if we run this again, it'll be a different pattern. Okay. So now we're able to display our grid. Now we got to do the hard part, which is really being able to update our grid in order to show off Conway's game of life. And so the way that we want to do this, right, is we want to create our function update grid. And we want to say, hey, for every cell, for each cell, what we want to do is count the number of alive neighbors and then update based on our rules. And that's it. Those 3 things are all we have to do. So we're going to be counting the number of alive neighbors pretty frequently, and just for the sake of organization, it might be nice to go ahead and put this in a different function. So before we write the code for that, let's talk about how we want to count the number of alive neighbors that a given cell has. And this might be just marginally trickier than you originally imagined. So if we're talking about, for example, this cell right here that I've just erased out, we're talking about this cell, then in order to count the number of alive neighbors, let me go ahead and move this for you guys. Okay, if we count the number of alive neighbors, we need to check 4 diagonals, and then also our 4 cardinals, north, east, south, and west. But if we're here, for example, then we can only check 2 cardinals. This cardinal off to the east and south takes us out of bounds, and so do their corresponding diagonals. The only diagonal that's available to us here is the top left. Now, if we take this cell in the top left right here, we're going to have a completely different set of alive neighbors. And so what we want to do is a little bit of error checking, right? We want to say, hey, let's try every single direction. If that direction is valid, then we want to say, hey, is this cell dead or alive? And if it's invalid, we'll just presume that it's dead. If it's invalid, then there's no cell to check. And so it cannot be an alive neighbor. Okay, so in order to do that, let's go back to our code. And we want to go ahead and create a function called countNeighbors. And we want to count the neighbors of some specific cell, which we've been representing using 2 values, their row position and their column position. Now, there are a bunch of different directions that we can go, and so maybe the easiest way to do this is a little trick that my friend Luke taught me. It is creating a 2D array that tells us the x and y positions of every single next direction that we need to go, every single one of our neighbors relative to our current position. So that'll make a little bit more sense when I write the code here. But the idea is, listen, we can go to the left, which is -1 in the x direction and 0 in the y, or we can go right, which is 1 in the x and 0 in the y, or we can go up, which is 0 in the x and 1 in the y, or we can go down, which is 0 in the x and -1 in the y, or we can go to the top left, which is -1 in the x and -1 in the y, or we can go to the bottom left, which is 1 in the x and -1 to the y, or we can go to the top right, which is, let's see, did I mess something up there? So this is top left, this is top right. Okay, yeah, this is top right, not bottom left, my apologies. Now we need to do the bottom left, which is -1 and 1, because we need to go down, and the bottom right, which is just going to be 1 and 1 here. Okay, so those are all of the directions that we can move in. And so now we can say, for every single direction that we go into, and maybe this is the hardest part of this, this code that we'll be writing, so we need to go in every single one of these directions, and we need to test out if there is a neighbor here, is it alive? And so we want to say if, we want to say the next position, right, this next row that we want to check, this is an integer, the next row that we want to check is our current row plus the x value of this direction. So it's going to be this direction's x value. And our next column that we're going to get is going to be our current column plus the direction that we're going into's first index, because that's going to give us that y value right here. And so we want to check, hey, is this row and column valid? And so maybe for now we pretend like this function already exists, but we want to say, hey, if is in bounds, if this row and column actually exists on our grid, because remember we could fall off of our grid depending on where we are and which direction we're going. If this next row and next column are within our grid, and our grid at that position, at the next row and the next column is alive, then it is one of our alive neighbors. And so we want to count the total number of neighbors that we have, and so maybe we create an integer to do that. We say num neighbors starts out at 0, but if we found a new alive neighbor, then we can increment the number of neighbors that we have by 1. And then at the very end, we return the number of neighbors that we've counted this particular cell to have. Oh, right. Okay, so if we're counting the number of neighbors, this needs to return an integer. It can't return void, it can't return nothing. And I think that's it for count neighbors. Now, we have yet to finish writing out this function, although it's a very easy function. We need a function called isIn that returns a Boolean. It tells us whether or not a particular cell is within our grid. This is taking in a row and a column. And we want to say, so when is a particular cell in? Well, we know that there are n cells with index values between 0 and n minus 1 for both rows and columns. So we want to return, hey, this row should have an index that is greater than or equal to 0, and this row index should be less than n, because we go from 0 to n minus 1 inclusive. And the same thing for the columns. The column index should be greater than or equal to 0, and the column index should be less than n. And if all of those things are true, then this is in, but if a single one of them is false, then we want to return false, because this is not in. It violates at least one of our constraints. Okay, and I think we should be good there. Any questions so far? How are we doing on time? All right, we're doing okay. All right, so now we want to go ahead and update our grid. So let's go back to that update grid method. For each cell, and again, this just means we want to use our double for loops here. So for int I equals 0, I is less than n. And then we want the same thing with our j's. We want to count the number of alive neighbors that this particular cell has, and then update its state based on our rules. So we can say the number of neighbors is equal to, well, let's just count the neighbors, right? We wrote a function to do exactly this. Let's count the neighbors for the cell at position ij. And now we need to update based on our rules. So what were our rules? Well, if this cell at I and j is alive, then we have a couple of different rules. And if it's dead, then we have other rules entirely. So if this cell was alive, there are two ways that it could die. The first way is if the number of neighbors is less than 2, if it has 0 or 1 neighbor, then it dies due to underpopulation. So we say grid at I and j now dies, it becomes false due to underpopulation. And I did not put a B in there for neighbors. Now the other case where a cell can die, right, is if it has too many neighbors. So if the number of neighbors is greater than, let's see, I think it was greater than or equal to 4. Let's go ahead and double check. Yeah, if it has 4 or more neighbors, then it dies due to overpopulation. So if the number of neighbors is greater than or equal to 4, then the cell at this position also dies. All right, now if this cell was dead to begin with, then the only way it becomes alive is if the number of neighbors, num neighbors, is exactly equal to 3. And in that case, our grid at I and j becomes true. And so that updates our grid. And that's it, guys. I think that should be good to run. Let's go ahead and run this thing. Okay, and yeah, we're getting something that looks somewhat right. And it's actually very nice that we got these two squares right here, because if we look at these squares, and you can do this validation for yourself at home, if you look at these two squares, indeed each of them should stay consistent. Every single one of these cells should remain alive forever. So we talk a little bit about interactivity. We don't have time to make this visualization interactive, but I'll post code that sort of shows how we can turn this into something that is interactive, where every time you click your mouse over a cell, it switches state from dead to alive. So you can start out by drawing some sort of initial state for Conway's game of life, and then you can see it run through. And so, of course, every time we run, right, we have a random initial state that we're starting with because of how we set up our function. And so that is going to give us a new result every single time. Now, the one thing that I will add, the one bit of interactivity that I will add, is it would be nice to be able to pause this and make sure that this is working as intended. So maybe we create a Boolean paused, and we say that we initially start out as paused. So we say paused is equal to true. And then we only want to update our grid if we're not paused. But if we are paused, we just want to display our grid, and that's it. And so right now we don't have a way of toggling between paused and not paused, so we'll go ahead and do that. We need to say maybe on a key press we switch between paused and not paused. And so the way that we can do that, right, in processing is using this void key pressed function that runs every time it detects a key press. And I won't be picky about which key you need to press to pause or play. We can just say if this function is run, then if we were paused before, be unpaused. And if we weren't paused before, then unpause, which is the same as pause. Yeah. And so we're just flipping the state that we were in every single time we press a key. So let's go ahead and rerun this. And I'll go ahead and press my key here, and that'll run, and it ended in that stable state. Now the cool thing, right, is that we can go ahead and scale up the simulation as much as we please. So if we do a 100 by 100 grid, and maybe we make this canvas just a little bit bigger to accommodate that, and we press play, I can stop it right here, press play again. There's all sorts of like very, very interesting stuff happening. And because this is a bigger canvas, things will take a lot longer to die out or find a steady state or anything like that. All right, so lots and lots of really, really awesome stuff that we can do with this process. We're not going to be covering every single thing that we can do, but the idea, the big take home here is that we're able to use this process in order to create cellular automata. And the only thing that you really need to change if you want to change the rules is going to be these rules down here from lines 43 through 50. Right, or maybe 49. And if you choose different rules, then all you need to do is mess with those like 6 or 7 lines, and you're off to the races. So Cellular Automata, lots of cool rules, lots of fun stuff to play with. We're having to breeze over it just a little bit. I'm showing you the foundational code, but we won't be messing too much with the what-ifs because we got to get to artificial life and Boids. So I'll post this code. Feel free to play with it to your heart's content. Let me go ahead and save it right now as Conway. Okay, so let's switch gears now and let's talk about artificial life. So now we want to be talking a little bit about Boids. So going back over to our whiteboard, or blackboard rather, going back over to our blackboard, let's think a little bit about Boids and how they work. I said that Boids were super simple. They are an artificial life form that mimics bird flocking, and they do so by moving around the screen in response to certain rules. So every single Boid, and we can think about them just as little dots for now. So we have a bunch of Boids around our screen. Maybe we have one all the way down here. Every single Boid has a couple of different characteristics. They have positions, and they also have velocities. So each Boid might be moving in a different direction with a different magnitude. So maybe we don't vary the magnitudes too much. Birds can't normally fly at variances between like 1 mile an hour and like 1,000 miles an hour, right? They sort of cap out at the same general speed if they're of the same species. And so we'll have them with all sorts of velocities that are different directions but are relatively similar in terms of their magnitude. Now, the thing that we want these Boids to do, the thing that separates them from our bouncy balls example, if you'll recall I drew something maybe a little bit similar with our bouncy balls in lecture 2, the thing that separates these Boids is that they respond to the Boids around them. And so maybe we talk about this Boid in particular right here. Maybe it has a viewing distance. It can sense the Boids around it within a certain radius. And maybe that radius encompasses these Boids. Now, if we want to make this ultra realistic, then every single Boid should be able to see only in front of it. It shouldn't be able to see behind it. But what we're going to create is a very simple toy model for Boids, just because that's all we really have time to do from scratch in lecture. And I think doing this from scratch has a lot more benefits because you really see how every single line is produced and the thinking behind every single line. So you can get super duper complicated. I've gotten super duper complicated with Boids. There's lots of fun stuff that you can do with them, but we're going to create a really, really simple toy model. So in this case, I think we were focusing on this Boid right here. This Boid can see all of the Boids within the circle that we've drawn here. Let me move this just a little bit higher up so there's no shadow. And it wants to apply each of the 3 rules that we talked about, separation, alignment, and cohesion, to its velocity. So how do we do that? Well, remember, separation tells us that we want to be able to stay far away from Boids that are a little too close to us, right? And so maybe if we're thinking about these Boids as objects, which is a very natural way to think about them, we've talked about them having attributes. Their attributes are position and velocity, and maybe these are both vectors. Let me zoom in just a little bit on this. Right, so they have 2 attributes that we really care about, a position and a velocity. And maybe they have a couple functions too. They have a function that tells them, hey, you have the ability to flock. We want to be able to see them, and so we want to say, hey, you have the ability to display yourself. And I think that's really all we need. We need the ability to flock, and we need the ability to display ourselves. So displaying yourself is pretty straightforward. What do I mean by flocking? Well, this is really where those 3 rules come in. Because we want to say, hey, we want you to adjust yourself. We want you to adjust yourself and your position, your velocity, as a function of the Boids around you. And so flocking says, hey, where are all the Boids around me? And then what is the separation? What is the alignment? And what is the cohesion factor that I need to apply to my velocity? And of course, my velocity then affects my position. And so that's what we're going to be figuring out. And we're going to be thinking about this very similarly to the way we thought about things in lecture 2 in terms of vectors. So before we talk exactly about how separation, alignment, and cohesion work, let's go ahead and create a general model for how our Boids will work. And for that, we'll move back to our processing sketch. Okay, so let's go ahead and create a new sketch. Let's go ahead and minimize out of this old one. And as always, we need a void setup function, and we need a void draw function. And we won't focus on these too much for the time being, because what we really want to focus on is that Boid object that we talked about creating. So we'll call this Boid, and of course this is going to be a class because it needs to be an object in the future. And if you're having trouble following some of the code that we write today, then I think your best bet is probably going to be going back to lecture 2, rewatching lecture 2, and then coming back to lecture 4, I think this is, in order to better understand this idea of classes and vectors and applying forces. So let's start by creating the attributes. As we said, we need the ability to know our position and our velocity, and both of those are vectors. Now the other thing that we need access to as a Boid is information about the Boids closest to us. Now, as we'll see, it's just easier to maintain a list of all of the Boids that exist in the entire screen, on our entire canvas, and then we'll prune out the Boids that are actually close to us, that are within our flock. that are within the Boids that we can see and care about. And so we'll call this list of Boids all Boids. We need a constructor for our Boids. And so let's think about what we might want for that. Well, we might want to take in an initial position for our Boid, just as we did with our bouncy ball. And then we need to get this list of Boids from somewhere, from someone. And so we'll add that as well to our constructor. So we want to take in a list of the other Boids around us. Okay, so we want to set our initial position to the initial position that's given to us. Maybe our velocity can start out somewhat random. This is going to be changed very quickly by our flocking behavior that we induce, but maybe we can say that our velocity is just initially a random 2D p-vector. Now the other thing that we want to do is set our list of Boids to the Boids that are passed in. And then the other prudent attribute that we didn't talk about on the blackboard, but that I think we need, is some sort of flock distance. So the idea is, hey, I want to be able to see like this Boid that's like 10 pixels away from me, but not that Boid that's 40 pixels away. What is the bright line? Like which Boids can I see and which can't I? We need to define a distance. Maybe we call that a flock distance, or flock dist for short, which is how far around me I can see, and these are the Boids that affect me. So we'll say flock dist is maybe we just start that out at 50. Now we also, like we said, want a way to display ourselves, and this we can make super simple. Better non-toy models of Boids, although I guess all Boids are toys in a way. Better models of Boids might display these as like triangles that like have a very clear direction, or they might use some sort of like 3D model. We're going to stay super duper simple, and we're just going to draw a circle. We're going to draw a circle at the X and Y positions that we know our position to be at, and then maybe we just have like a size of 10. And so that's going to be super simple. Now, we also want to create our flocking behavior, right? And this is going to be where the meat of where we spend our time with this sketch is going to be. And so for our flocking behavior, really we want to do a couple of things. The first thing is figure out the separation, alignment, and cohesion forces. So separation pushes us in one way, alignment pushes us in one way, and cohesion pushes us in one way. We need to figure out where those forces are pushing us. And then the second thing that we want to do is weight our forces. So it might be possible that separation is really, really important for our Boids and they want to stay far away from each other at all costs, or they're really focused on being aligned in the same direction. They want to make sure that they absolutely go in the same line. And so messing with Boids and like having this what if parameter at our availability gives us the ability to change how important each of these forces are to our Boids. And that's going to be pretty important. Now the third thing that we want to do is apply these forces to our velocity. And then finally, the most important part of flocking is, of course, updating our position. Okay, so now let's go back to the board and let's talk about how the separation, alignment, and cohesion forces work. Let's start with separation. So in order for us to be separated from the other Boids, what we really want to do is say, hey, if I'm focusing once again on this Boid, I want to say, hey, of all of these Boids, which ones are visible to me? And maybe just the ones within the circle are visible to me, so they're the only ones that matter. And so I'll say, hey, you're inside of my circle, so you matter to me. I want to move away from you. I want to move the opposite direction as you. And so I want to calculate the difference of the vectors of their position and our position, right, and that will give us a force pointing in the opposite direction of where they are. And so that's going to be useful to us. And so for maybe like a clear example of this, if we have someone that is very close to us, maybe we introduce a new Boid, he's coming in from right here, maybe this forces us to go in the opposite direction of the way that he's coming at us. And so we can just use very simple vector subtraction in order to calculate that value. Now, the other thing that's important with separation, right, is that we don't just want to say, hey, this Boid is close to me, so I want to go the opposite direction of it. This Boid is somewhat close to me, I can see it, so I want to go the opposite direction of it. Think about this maybe the way that you might think about driving a car. If you are driving a car and you can see a car that's maybe 500, 1,000 feet in front of you, and you have a car that is maybe like 2 feet or 3 feet to your right, you're going to be a lot more concerned about the car that's a couple feet to your right than you are about the one that's super far in front of you, even though you can see both, right? And that's going to be really important, because what we want to do is we want to say, hey, not only does it matter that we can see each of these Boids, but we want to proportionately change this force based on how close the other Boid is. So it's going to be a lot more important to us that we avoid this Boid right here than we avoid this Boid right here or this Boid right here, right? And so that is going to affect how we do this calculation. All right, that being said, let's go back to our code and we'll figure out exactly how this works. So I think the easiest way to go about this is to create 3 different methods, one that figures out our separation force, one that figures out our alignment force, and one that figures out our cohesion force. And so each of these should return a force, they should return a vector, and so we'll create one for separation, another one for alignment, and another one for cohesion. Okay, so how do we want to work with separation? Well, we want to say, hey, for every single Boid, the first step that we want to do is figure out which ones are close enough to us that they matter. Now, how do we want to do that? Maybe we actually separate that out into a function of its own. So maybe we'll say Boolean in flock. And so a different Boid B is within our flock if they are within the flock distance of us. And so an easy way to calculate distance is, of course, we know we use distance formula in lecture 2, and we did that, I'm not sure if we did that exactly with vectors, but we used the dist method. Now we're going to be using the p-vectors dist method, which is just a little bit easier. It calculates distance formula using 2 p-vectors as input. And so we can say the float distance between us and Boid B, which we're passing in, is p-vector.dist of our position and B's position. And we want to say, hey, if this Boid is too close to us, or if this Boid is within our flocking distance, if it's close enough that we can see it and consider it part of our flock, then we want to return true. If we want to return, this dist has to be less than or equal to our flock dist. Now there's one other thing that we need, right? And that's going to be that we can't just include everything in here because our list of Boids includes ourself. And so we want to say, hey, I'm obviously part of this flock. I'm part of whatever flock that I'm in, but I care about the other Boids around me, so I don't want to include myself. And of course, we talked about this a little bit in lecture 2. We can say that our distance from ourself is 0. So our distance from us and the other Boid has to be greater than 0. The other Boid can't be us, but it also has to be visible to us. And so if both of those things are true, then hey, they're part of our flock. Boid B is part of our flock. Otherwise, they are not part of our flock, and we don't want to consider them. Okay, so we'll go back up to separation. So, of course, separation is a force. We want to be returning a force. So we'll create a p-vector called separation force or set force for short. And we'll initialize that to be 0, 0. Now we want to say for every single Boid B in our list of others, we want to say, hey, first of all, do we care about this Boid at all? Are they visible to us? And so really what we're asking is B in our flock? And if they are in our flock, then we will actually want to do stuff with them. We actually want to figure out what they contribute to us. Otherwise, they're not relevant. And so we want to say, hey, if Boid B is actually within our flock, then we need to figure out the opposite direction as them. And like I said, this is going to be super simple. This is just going to be vector subtraction. I'm going to say the P vector opposite direction is going to be the subtraction between our position and their position. That's going to give us the opposite direction as them. Now remember, we want to weight this value. We want its magnitude to be a function of how close they are to us. And so in order to do that, we need to normalize this function and then weight it by its proper amount. So how do we want to weight it? Well, the closer that a different Boid is to us, the more that they contribute to us. So if we take our opposite direction vector and we divide it by the distance, that's going to inversely weight the distance with the magnitude of the vector, right? The closer that they are to us, the smaller that denominator is going to be, which means the overall amount is going to be bigger. And so we can say our opposite direction gets divided by the distance between us and this other Boid. And finally, we want to say, all right, we've calculated the opposite direction. We've calculated how important it is that we move away from this Boid. We need that to contribute to the overall separation force. And so we want to say set force dot add whatever this opposite direction vector was. And now at the very end, we need to return that, right? We need to say, all right, we've calculated what our separation force should be. Let's return that. But we don't just want to return it. Remember, between separation, alignment, and cohesion, we might get vectors of all sorts of different magnitudes, and we want to weight them ourselves. We want to choose how important each of them are. And so we'll normalize our separation force before we return it. This should be Boids and not others. All right. Any questions so far about anything? Everybody cool with the idea of separation? All right, let's talk about alignment, and then we'll talk about cohesion. Alignment is super duper easy. Let's go back to our whiteboard. And so remember, the way that we want to mess with alignment is, again, we're using all the same ideas as before. We only care about Boids that are within our flock. Alignment is really us saying, hey, we want you all, or we want to move in the same direction as all of you. And so we just want to figure out what the vector looks like that has everyone else's velocities in it. And if we're able to take everyone else's velocities and then normalize that, that tells us what direction we want to go into as well, what our velocity should be. And so this is going to be super simple. We just want to find everybody else's velocities, add them up, normalize the value. So let's go back to our code. This is going to take like very, very few lines to write. We want to say we'll create an alignment force that initially starts out as 0, 0. Now we want to say the exact same thing we said before. For every single Boid B in our list of Boids, we want to ask ourselves, hey, do you matter to us? Are you in our flock? And if the answer is yes, then we want to say, okay, shoot, yeah, you do matter. Let me add your velocity to my running alignment force. And then at the very end, I want to say, okay, I have everybody that matters to me alignment, I have their velocities, so I want to return that force normalized. Everybody cool with that idea? All right, awesome. We're very close to being done with the hard part of this lecture. Let's go back to our whiteboard, blackboard now, and talk about cohesion. So cohesion is going to be relatively straightforward. We want to move to the center of our flock, right? That's going to be really, really important to us. And so the way that we figure out the center of our flock is we want to say, hey, who's within our flock? Let's get y'all's distance. And once we have your distance, let's calculate the, position. Let's get everybody's position. And let's calculate your average position, because that's going to be the center of the flock, the average position of everybody in the flock. And so maybe if we consider the positions of all of these Boids around us, we'll figure out that, hey, we really want to be here. This is where we want to go. And so what we want to do is create a vector that points in that direction. It really should be straight. It should be a little bit like that. And we want to push ourselves towards the center. And of course, the way that we do that is, again, vector subtraction. So how we will do this in the code is we'll say, hey, if you are important to us, if you're within our flock, we'll add all of your positions to a vector, and then we'll divide that vector by how many of you there are. Let's calculate the average, right? So we need to sum up all of the positions x's, divide by the number of people in our flock, same for y, and then we'll create a force going to that center. Any questions about that idea? All right, awesome. So let's go ahead and do exactly that. For cohesion, let's go ahead and create a p-vector called cohesion force. That's going to start out, just like everything else, at 0, 0. And we'll say, all right, for every single Boid B, in our list of Boids, if you matter to us, if you're in our flock, then we want to consider your position. And so remember, we said we not only need to keep track of how many, what the positions of all of these Boids are, but how many are in our flock. So we'll keep track of num in flock. We'll start that out at 0. And so we'll say, if you're in our flock, hey, we have another person in our flock. So we'll increment that value. And then we'll take your force and add it to the running cohesion force that we have so far. Right, and then when we get down here, we want to say, all right, if there are more than 0 people in our flock, we don't want to divide by 0. If the number of Boids in our flock is greater than 0, then we want to take our cohesion force and divide it by the number of Boids that are in our flock. What doesn't it like? Num in flock doesn't exist. Did I misspell something? Num in flock. Okay, must have misspelled something. Variable num in flock does not exist. What have I done here? Int num in flock definitely does exist there. Let's ignore this for now. I don't like ignoring error messages, but let's ignore this for now. I'm not sure what it's talking about off the top of my head. So let's ignore it for now. And then we want to say, really, that we want to get the vector that is pointing towards the position co-force. And so in order to do that, we can go ahead and return our cohesion force we can go ahead and return our cohesion force dot sub our current position. And I think that should be good. Oh, and we need to normalize that, as always. Okay, that is somewhat concerning, but we will come back to it. Oh, okay, you know what? I think this error message says num in capital FL. Maybe that's just what I had before, and it's not updating properly. Go ahead and delete this line, and then put it back in. Okay, it still doesn't like that. and it's still giving us the same error message. Okay, I really don't think it will bug out, hopefully, but we'll cross that bridge when we get there if we need to. Okay, so we figured out how all of our forces work. Now we actually need to apply them, right? And so we'll go back up all the way over to our flocking code once more, and we'll say, all right, the p vector for separation, which I'll just call S to abbreviate it, is whatever sep the function gave us, A is whatever the function align gave us, and C is whatever the function cohesion gave us. So we've done step one. Now we need to weight each of these forces, right? Remember, all of them have the same magnitude right now, and so we can multiply them by some weight value. For now, I'll just say all of them have the exact same weight, which is 1, sorry. All of them are equally important. And we're done weighting our forces. Now we actually need to apply these forces to our velocity, and so we can just say velocity.add our separation force, velocity.add our alignment force, and velocity.add our cohesion force. Now, the other thing that we want to do is, remember at the very beginning, we said that all of our Boids should have somewhat similar magnitude, or like magnitude of velocity. And so we want to limit the overall magnitude. We don't want to get it too big so that there isn't too much variance between the velocities of each of our Boids. And so we'll say velocity.limit 2. And so that will limit our Boids velocities. And finally, to update our position, we just take our position and we add the velocity. That's something that we've done a couple of times in our lecture 2 example. And I think that should be everything on the Boids. This is still somewhat concerning to me, but that's okay. Let's go back over to our setup and see if this process works. So we want to start by creating a list of Boids, right? We're going to have a bunch of Boids on screen. We'll call this our Boids. We also want a particular number of Boids on screen, and so we'll say num Boids is equal to how many Boids we want on screen. We can go ahead and set this as full screen, and we can say that num Boids maybe is equal to 100 to start with, and Boids is a new array list. Now, we want to add 100 Boids to our list, which is currently empty. So we'll say for int I is equal to 0, I is less than the number of Boids that we have. We can say Boids.add a new Boid, and we want this to have a random start position. So we'll start it at a new p vector with a random x and a random y. And we also need to pass in, remember, our list of other Boids, which is just going to be Boids. Go ahead and close that off. And I think we're off to the races. Now, we always want to clear our screen before each frame. And maybe we want to say, for every single Boid be in our entire list of Boids, we want to say, hey, Boid, you should start by flocking, and then you should display yourself. So b.display. Okay, and I think that should be pretty much everything. Let's go ahead and run that, see what happens. Okay, it did not like this. And so you know what I'm going to do, and this might be not great practice, but I'm not sure that we even need to divide by the number in our flock, because this ends up getting normalized anyway. I don't think it'll matter too much, but we'll see. Okay, so yeah, it looks like this is working. We have Boids that are moving around on our screen. They're picking up different Boids as we go. And okay, we're getting a little bit of what might be buggy behavior because we just saw one Boid like move off screen. But we sort of have something that, you know, in a way resembles bird flocking behavior. Now let's make a couple of quick modifications. The first modification that I want to make is I see that a lot of Boids are moving off our screen and they just never come back onto our screen. And so the super simple change that I want to make is if you move off the left side, then you come back on the right side. And if you move off the top, then you come back on the bottom, and the opposites of each of those. And so we sort of have like this infinite playing field for our Boids to move along. And so doing that should be a very simple process. All we want to say is that in order to update our position, we will say that if our position's x value has suddenly moved off the left side of the screen, if it's less than 0, then we'll reset it at the right side of our screen. Otherwise, if our x position has moved off of the right side of our screen, then we want to reset it on the left side. And we want to do the same for our y. If our y position has gone off the top of our screen, then we want to reset it at our bottom. And if it's gone off the bottom of our screen, then we want to reset it to our top. And let's go ahead and rerun that. Okay, and we get some really nice behavior. Remember, all of these started with random velocity, and now they're sort of moving in a very straightforward pattern. And they're moving in a way that, makes a little bit of sense to us. If you were to look up at the sky and see Boids flocking in this way, it would definitely make sense. Now, in order to prove to ourselves that this is working, let's go ahead and mess with some of our parameters, right? The really cool part of all of this is that we have forces that we can weight. I think a really easy way to show that maybe this is working is we weight our separation to be pretty high. So separation is really important, and if we put a bunch of Boids on screen, what you'll see is really, really interesting, right? The Boids don't care about moving in the same direction. They don't really care about moving at all. They care about being as far separated from each other as they can. And that's going to be really, really important because it tells us that if we mess with these parameters, we might get different types of flocking behavior. This is just another what if that we can change in order to create all sorts of very, very pretty patterns. All right, so we've got around 8 minutes. I want to tell you guys a little bit about what we can do with these Boids, how we can extend these ideas before we wrap up. We haven't gotten a lot of chance to play with what ifs today during lecture, just there's so much content that we had to pack in. So that will probably be a bigger part of our assignment. Before we do that, maybe let's play with just one what if. You guys know I love playing with color in these visualizations, and so maybe we drop our number of Boids back down to 100, and maybe we color our Boids based on where they are on screen. And because they will often flock together, coloring them by their position on screen will almost color them by their flock, which is a pretty cool thing to see happen. And so the way that we want to do this is super simple. We want to mess with our display function, and maybe we just say, hey, the fill color for each Boid is going to be a function of their x and y position. So remember, we're talking about RGB normally. Let's change this color mode to HSB. So we'll mess with our hue, saturation, and brightness, and we'll say, hey, our hue should be a function of our x position. So our x position can go anywhere from 0 to our width. Let's map that to a value between 0 and 255. And our saturation maybe should be a function of our y position. And so that's going to be between 0 and our height, and we'll map that between 0 and 255. And as far as our brightness goes, maybe our brightness is always pretty high. That might be nice because we are working on a black background. Let's go ahead and run this thing. Okay, yeah, and we definitely get some pretty interesting results here. It looks like we're all moving towards sort of the same direction in this case. I wonder if I changed my parameters or anything like that. But we do see like flocking behavior that is, I guess in this case, not very focused on color because they are all moving in the same direction. That might be because of that little bug that we had down there with cohesion. And I'll go ahead and take another look at that I don't think it's a big enough deal that it ruined our visualization, but I do want to make sure that we know exactly what's happening there. So I'll go ahead and post in Slack exactly what changes we needed to make in order to make that fix. My assumption is, oh, you know what, guys? That L was capitalized. I was looking at the if statement and not at the rest of the statement. Okay, so that should change that right there. Okay, so it turns out that was the mistake. So that makes sense now. All right, okay. We'll not worry so much about separation anymore. Let's go ahead and give this thing one last run while I tell you guys a little bit about the interesting stuff that we can do with Boids that we haven't talked about entirely today, and we'll sort of see that Boid emergent behavior in its most natural, beautiful form here. Okay, so what can you do with Boids that we haven't done here? Well, the most important thing that you might notice is that we have been using, for all of our Boids, just circles, which is totally fine for now, but it might be nice to give each of these Boids sort of a better shape, like a triangle. And the really important thing that comes with using triangles is it gives us two abilities. One, we can tell exactly where a Boid is headed. We can tell very clearly what its velocity is. That's important to us just in terms of debugging, honestly, because it tells us that we know where each Boid is going and that it's going in the right direction, but it also looks just a little bit prettier. The other reason that using Boids as triangles might be important, and Daniel Schiffman has a great lecture where he sort of talks about this and considers it, is we want our Boids, right, to be looking forward for other Boids. And so if there is a Boid that's over here, even if it's within our distance, within our sight, we should be able to see this Boid, but not be able to see this Boid. And so that's an important consideration to make. And I realize there's a little bit of a shadow there. Let me move that up even more. It's an important consideration to make because it makes this process all the more realistic. All right, so we'll go ahead and close off lecture with that. Thank you guys for bearing with me. I know this was a faster lecture. The next lecture is going to be a little bit slower, and then after that, we're pretty much done with the course. So I'll get this posted as quickly as possible so that you guys have easy access to it in case you want to rewatch something, take a look at the code, and all of that code will be posted as well. Other than that, thank you so much for coming, and I will see you guys on Wednesday.